Hi, I'm George Huffman at NASA Goddard Space Flight Center, where I'm the Deputy Project Scientist for Global Precipitation Measurement Mission, or GPM. There's my email if you'd like to contact me directly. Thanks for stopping by my virtual Hyperwall poster, and I'd like to spend a few minutes talking about keeping watch on the weather with NASA precipitation data. GPM is a joint Japan-US satellite mission which is dedicated to understanding global precipitation. One key tool is the so-called Core Observatory. This artist's depiction of the Core Observatory on orbit demonstrates the two instruments that it carries. There's a dual frequency precipitation radar, frequencies of Ka and Ku, that give you a three-dimensional cube of data, and there's a passive microwave instrument called the GPM microwave imager that gives you a two-dimensional picture through the atmosphere. As the orbit goes down track, it records both sets of data over a relatively broad swath for GMI and a narrower swath for PR. But when you look at the globe as a whole, Core Observatory is pretty lonely. It's an inclination orbit of 65 degrees, and you get something like one look a day from the GMI and less than that from the radar. So we invited the other agencies that have passive microwave instruments to contribute their data. All of these other satellites have their own missions, but their data are also useful. Even when you take all the data, you don't have observations more than about once every 3 hours. And so the final step is to interpolate in time to give you an estimate every half hour, a product that we call integrated multi-satellite retrievals for GPM, which is a product that I lead. What can you do with this? Well, here's an example of iMerge for Hurricane Zeta, which is just coming onto the Gulf of Mexico. The bright colors are rain, the blue colors are snow. And at some point, there's an overpass by the Core Observatory, 20th of October, about 8:40 UTC. Same color scheme, now in 3 dimensions. You see the banding structure extending right up through the entire layer of precipitation, and now we'll slice through the storm and give you a view. That donut hole in the middle is the eye of the storm. As it comes back, notice how there are higher reflectivities at low altitudes, which is typical of the way tropical convection works. In addition, notice the blue colors at the top. Even though this is the tropics, that's snow. Yep, snow. So it snows a lot in the tropics. You just have to go up 4 or 5 kilometers to find it. Notice as well the squall line, which is up to the northwest, or rather northeast, which also has snow at the top. It's very typical of the way deep convection works. Another thing we can do is to take other data sets and compare it to precipitation to get a better idea of how the Earth system works. This is an illustration of the summer monsoon in South Asia. The cloud picture is like you see on TV every night, the infrared from geosynchronous satellite, but now we can lay on top of that the iMerge rainfall estimates over both land and sea, so you get a continuous picture regardless of what the underlying surface is, not like land-based radar that stops at the coast. You see lots of convection over the Bay of Bengal and then moving on to the Indian subcontinent and Southeast Asia. When you get these summer rains, you get lots of soil moisture, which is shown in the shades of green. Soil moisture is important because it enables the agriculture, which allows the human population to thrive, and it also indicates that you have enough water, most likely, for transportation and other water needs. Of course, when you get too much rainfall, it floods. The blue shades give you a sense of where there's thin but widespread flooding, and then the brighter sort of magenta colors, that squiggly line across central and eastern China, is where the floods have concentrated into the main stem rivers. Another side effect of getting too much precipitation is landslides, which are shown by these little symbols. These are observations of landslides during this summer monsoon season, and they tend to be concentrated in areas of complex topography and heavy rainfall. You sort of need both effects to give you the landslides. One really cool thing you can do is a split screen with the summer on the left and the winter on the right. The little arrows tell you the wind flow near the surface. In the summer it's onshore, in the winter it's offshore. These wind flows bring moisture onto the land area in the summer and dry air off of the land in the winter. Fundamentally, these are driven by the temperature differences between land and ocean. Air rises over the warmer feature and sinks over the colder feature, which is what drives the horizontal wind flow that you see near the surface. Besides looking at just the original area where we have the monsoon, scientists have realized that there are monsoons in other places, and we can use our global data sets to eliminate those. For example, in West Africa, in the summer, the temperature gradient is between the Atlantic Ocean to the south and the Sahara Desert to the north. You see the blobs of convection moving across West Africa. These easterly waves move out onto the ocean and sometimes drive hurricanes in the Atlantic basin. Another area where you have a summer monsoon is a North American monsoon. It starts in northwestern Mexico and shown with a soil moisture excess here. And as the summer moves on, it moves up into the southwestern U.S. Finally, there's a monsoon which takes place over Australia and the maritime continent in their summer, the northern hemisphere winter. Here, the land-sea contrast is between the ocean to the north and Australia primarily, and it's sort of one half of the giant monsoon conveyor belt that goes from Southeast Asia all the way down to Australia, here moving air from north to south across the equator. Another thing that we can do with iMerge is create composites of the diurnal cycle. So you see the afternoon maximum in Florida, which is typical if you've ever been there. There's a nighttime maximum over the ocean nearby. But in the Midwest, there is a different cycle which has convection blowing up on the eastern slopes of the Rockies and moving across as the night wears on, so that by the time you get to Iowa, the maximum in convection is actually sometime around midnight. Finally, I'd like to illustrate the global perspective that iMerge provides on precipitation for this week in November of 2020. It shows the typical weather around the globe, the ITCZ near the equator, and the subtropical highs north and south of that, and then the storm tracks at mid-latitudes over the Kuroshio Current and the Gulf Stream and the Southern Ocean. As well, this shows Hurricane Iota crashing into Nicaragua as a Category 4 just 2 weeks after Eta hit in almost exactly the same spot. These global data show how the weather works around the world and gives us insight into the dynamics of the atmosphere. All of the data are free for use from the GPM website shown at the top of the page, and updates to this movie are made every half hour at the address at the bottom of the screen. As well, my contact information is shown there if you want to send me an email. Thank you.